Hello, YouTube. Today we're just going to do a couple examples of some problems from the 1D and 2D motion units, just because students sort of requested it. So here it is. This is Unit 1 examples. So we're going to start off with a 2D motion and like relative reference frame shift type problem. So let's say we've got a river and we know that you have a boat which goes 10 meters per second in still water. Crosses a 20-meter wide river in the minimum amount of time. Drifting. I have to be careful about this. Let's go with 12 meters in the process. What is the... actually, let's put it in a direction. East. Quickest the boat can get to a point 12 meters west on the opposite bank. From that start point. So, drawing it out. We've got this river. We know that the width of the river is 20 meters. We know that when the boat takes its minimum time to go across, the boat winds up in this location here. 12 meters to the east. So this is situation 1, and in particular for problems like this, where you've got a couple of different things going on, really important to keep track of. This is situation 1, this is situation 2. Are there things that are going to be in common between those two situations? Can I set things up so that I've got equations going for each? So thinking about situation 1, figuring out as much as I can about situation 1, and then we'll worry about situation 2. So for situation 1, they said minimum time. And so let's take a second, think about what the minimum time we can have to cross this river is. Well, the only thing that matters for crossing the river is getting from this side to this side. How far we go sideways does not matter at all. Now, what we can't control is getting this boat to go faster. We can't make the boat go faster than 10 meters per second. We actually also can't make the boat go slower than 10 meters per second. What we could do is change the way that the boat is pointing. So if we want the minimum time, we need to point the boat so that we're going such that it will take as little time as possible to get across the river. This pen shouldn't be dead. Yeah, there it is. Which means we want as much velocity in this direction as possible. Well, the river, based on how this is drifting, is going to wind up going this way. So if we want to get as much vertical velocity as possible, the only way we can do that is just point our boat vertically. So minimum time, again, because we want the biggest vertical velocity component as possible, means we should try to get as big of a vertical velocity component as possible. So we know that this, the velocity of the boat, is going to go straight up. Now, if we take these two and we add them together, what the boat is trying to do plus what the river does to the boat gives us what the boat actually does. So in this case, we've got the velocity of our boat going up. We've got the velocity of the river going to the right. And when you put those two together, you'll get the actual velocity of the boat in the river, which would be the velocity of the boat with respect to like the ground. So like there's a person over here who's watching it. And that diagonal, is why we drift downstream. So what are some things we can figure out from here? Well, if I list out all my givens, and actually, you know what, before we fall down that rabbit hole, we've sort of figured out what the situation is. We have a clear idea of what's going on with it. Before we start doing math at it, let's figure out what math we need to do. Looking at situation 2, what's that situation? What is the quickest the boat can get to a point 12 meters west of on the opposite bank? So for this one, we've still got our river, but this time we want our boat to go from here where it starts over to here, which in this case has 20 meters going north and 12 meters going west. So we need our boat to point for the actual velocity that the boat does in a straight line at the point. Because if we go any other way, we'll have to either backtrack towards the thing or backtrack away from the thing, which means we'll have to travel a larger distance, which means it should take longer to get there. So a direct line straight path is going to be the thing that is the shortest amount of time here. Or our quickest the boat can get to that point. Now, this red arrow is the velocity of the boat with respect to the ground for our second trip. The river is going to be a velocity vector here. So if I'm looking at the components of this arrow, one of the components for this arrow is going to be the river. The second component for this arrow, which actually I put in the wrong spot. The second component of this arrow is going to need to be the velocity of the boat. Using these two together, we need to make this vector. And we can use that to figure out how big that vector is going to be. Yeah. Before we can do that, we need to figure out before we can do that, and I just realized this problem is going to be a little more complicated on the algebra than I had originally intended, but I think it's probably fine. Yeah. I'll try not to get too lost in the weeds of the math on this one. And I'm not going to make the next one as hard as I was originally going to. So if we want to do this, it would be really helpful if we knew the velocity of the river, right? And it would also be really helpful. Yeah, I mean, that's the big one. We can't really do this if we don't know the velocity of the river. We're also going to need to figure out how we want to point the boat so that we can get the angle on the velocity of the river correctly so that we can figure out how long it takes to cross the river. And there are a few ways you could go about doing that. Okay. So to start with, we're going to need to figure out the velocity of the river. Well, if I look at situation one is something where I know more stuff. I know which way the boat is pointing. I don't know which way the boat is pointing here, so I'm going to leave off from that one until I have more information. Using that the boat is pointing straight across, and that's the only velocity in the y direction, we're pretty much going to have a setup where it's like, what's the stuff in the y direction? What's the stuff in the x direction for our first setup? Well, in the y direction, our velocity is just the velocity of the boat, which was 10 meters per second. Our displacement in the y direction is 20 meters. For the x direction, we've got our velocity, which is just our velocity from our river, whatever that is. We also know that our displacement in the x direction is 12 meters. Now, if I wanted to figure out this velocity, I could do it, but the equation would be that the velocity for our river is equal to displacement divided by time, because this is all constant velocity stuff. So if that's the case, I'm going to need the time before I can do that. As luck would have it, the time it takes to get across the river is the same amount of time that it's drifting down the river for. So let's see if I have more information over here. Well, I know the distance and I know the velocity. I can use those two together to get the time. So once I've got the time from the y direction in this situation, which is the part I know more information about, I can use that time with the x direction to figure out the velocity of the river. Then I can bring that over to situation 2 and maybe have enough information to figure out some stuff about situation 2, because the velocity of the river is the same in both cases. Alright, so actually doing that, we know that our time, our displacement divided by our time is going to need to equal the velocity. Multiply each side by time, multiply each side by time, divide each side by the velocity, divide each side by the velocity. Our time is going to be equal to our distance divided by our velocity. That should be delta y, which is 20 divided by 10, or 2 seconds. So it takes us 2 seconds to cross the river. Take that and bring it over here, and we'll get that it's 12 meters, and we're dividing that by 2 seconds, which means that the river is going 6 meters per second east. So now I've got the velocity of the river, and I can take that velocity of the river and bring it over to my second situation. Our core parts so far. We have 2 directions that things are happening in. Arguably 3. There's a few ways you can think about this. We have 2 situations. We're dealing with just the first situation because we know more stuff about it to start with. Using that first situation, we saw the key word of minimum time to cross the river. The minimum amount of time happens when we have the biggest possible velocity. We have the biggest possible velocity when we point directly across the river. So we point directly across the river. That's our y velocity. We use our y velocity with our distance to figure out our time. Now that we've got our time, we can use that time with the distance we drift, again using constant velocity equations, to figure out how fast the river is going. Now we can start thinking about situation 2 in more detail. So getting a larger picture of the vectors, we know that if we take the velocity for the boat and we add it to the velocity for the river, we're going to need our final velocity vector, which we get by putting the components of those two things together, to point straight at the point that is 12 meters down the river, which is 20 meters wide. So this is going to be an angle. This side length is going to be 10. This side length is going to be 6. I need the angle from this thing to match the angle of the displacement I want. Because the velocity and the displacement for the final velocity and the final displacement, both of which are diagonal, will match. The size of the components will match as well. So there should be the components of this vector are going to be a y component and an x component. If we're looking at our picture and we break our boat vector up into components as well, this component is going to be 10 times the cosine of phi. We're going to do a phi measurement for this angle because we now have two angles. You could do theta 1, theta 2 if you rather, but I'm going to use phi. Cosine because it's adjacent. For this one over here, it'll be velocity of the boat, which was 10, times sine because it's opposite. Great. If I look at these components, our components here for the x direction and our components here for the y direction will let us set up two equations. I know that my velocity in the y direction will need to equal the sum of everything in the y direction, which is just 10 sine phi. The problem with this is that I've got no idea what Vy is. But I could represent it using, that actually doesn't, yeah, that'll work. I could represent it using that it's going to share the same angle as this one. So I'm actually going to call the smaller angle theta, not the bigger angle theta. This angle here that our displacement vector makes, which we can figure out using trig, is going to be the same as the angle for the final part of our velocity vector, because our velocity vector, our triangle of velocity vectors and our triangle of displacement vectors need to be similar triangles for constant velocity. This doesn't hold for something like a projectile where one of them is accelerating, so one of them is changing. But if you're moving in a straight line, your velocity has to point in the same direction as your displacement and be proportionately sized for the components of each. So what we can say is that Vy is actually going to be the velocity of the boat with respect to the river times the sine of theta. Cosine. That's the adjacent one. And we can set up something similar for Vx. For Vx, it's going to be the velocity of the boat with respect to the river times sine of theta, because this one is opposite to this angle. Despite me trying to do a second, neater version of the picture that's larger, it got kind of messy. Our velocity for our boat should look something like this for the final results, where this is the velocity of the boat with respect to the ground. Those should both be G's. And this is the y velocity here, and this is the x velocity here. This is our theta. This is our 20. This is our 12. This is our actual displacement vector. Well, that needs to equal Vx. But Vx also needs to be equal to the sum of the vectors that make it up, right? There's this x component from our boat. There's this x component from our river. They need to add up to equal Vx. Now the boat goes backwards, so I'm actually going to go ahead and pop a negative in front of it. Negative 10 times the cosine of phi. Plus the velocity of our river Great. So at this point, we have two equations and we have three variables. No, we don't have variables. Sorry, we know theta. So we have two equations, two variables. The velocity of the boat with respect to the ground is one variable. Phi is our second variable. We actually already know what theta is for this if we do a little bit of work using these two side lengths. We need this angle. We have the opposite and the adjacent. So theta is the inverse tangent of our opposite, our 12, divided by our adjacent, our 20. And just for the sake of not having to write a bunch of symbols for this one, I am actually going to do inverse trig and get an angle. There we go, accidentally did the tangent. Which is actually horrifically close to 30 degrees. So I'm just going to call it, now it rounds to 31, whatever. 31 degrees, fine. So 31 degrees is our angle here. We don't need to know phi. What we need to know is, oh god, this is gonna get really messy. Oh well. Sorry, we don't need to know phi. What we need to know is the velocity of the boat with respect to the ground. In particular, because what would be really useful for us is to get either Vy or Vx. Once we get Vy or Vx, from there, what we can do is the same thing we did here to get the time, just with these numbers instead for this part of the situation. Whew. Part 1 would be a reasonable question, by the way. Part 2 would not be like the first half of what we did with the first situation, reasonable question. This second half, probably an unreasonable question, just because of the algebra that's about to happen. So doing it out though, I need to eliminate phi because I'm not going to care about phi. If I'm not going to care about phi, easiest way to solve for it is to divide each side by 10 from this equation, divide each side by 10 from this equation. That'll give us coming down here that sine phi is equal to VBG times cosine of theta divided by 10. And I need to take the inverse sine of both of those sides. Oof, this is going to be really messy for the algebra. This system is solvable. It's going to take some trig identities that are not immediately obvious to me. If we were plugging over here and getting a if we were plugging in over here and getting a sine, that would undo the inverse sine and that would make it pretty straightforward. If we had a little bit different information, this thing could be a lot easier. So in particular, if I'd given you the angle that the boat was pointed at instead, like if I'd given you phi and asked to find the time it took to cross, you wouldn't have had to bother finding the velocity of the river. So like given you phi and asked where it lands, that one would be a lot easier and probably fair game. I think I'm just going to call it on this part. Again, I don't want to get too lost in the algebra. This one's already been 25 minutes. Bummer. Let's go to a projectile problem, and I'll just make sure that I make the problem easy enough that it's not a big deal. All right. No, let's do it this way. I launch a ball at a 30-degree angle from a cliff that is 15 meters tall. It lands 2 seconds later. How far is it from the base of the cliff? Does that work? No, it needs to land at least 3 seconds later. So let's make it 3 seconds later, and I think that'll make the numbers work out nice and easy. All right, great. So setting up a picture, getting our variables squared away, and then solving things out. This is a projectile problem. We have things that are going through the air, so gravity is going to be pulling them down. That'll come into play. Picture. My cliff is 30 meters tall. I'm looking for delta x as my final goal. I know that I'm launched at some initial velocity, don't know what, but we do know that it's a 30-degree angle. And that's pretty much it. Great. Let's set up our x, let's set up our y. In particular, the thing that's really nice about these types of problems is that there's always going to be that separation. And so as long as you're keeping track of everything from both, you can use information from one to relate to information from the other if you have something that ties them together. A thing that tends to do that, an angle. Angles are great for tying things together. Time, that's the other big one. One of those two. So for our x, we don't know what our displacement is, and that's our sort of final big variable, so we just leave it as a variable. Our vx is related to our initial velocity, so I'm just going to go right ahead and break this thing up into components. Our vx is going to be v naught times the cosine of 30 degrees, whatever v naught is. Our time we know is 3 seconds. Coming over to the y, we know that our displacement in the y direction is negative 30 meters. Why did I say 30? Sorry, it's a 15-meter tall hill. Negative 15 meters. We know that our acceleration in the y direction is gravity going down, so I'm just going to do negative g. We know that our initial velocity in the y direction is v naught times the sine of 30 degrees. And we know that our time is, once again, 3 seconds. So if I'm looking at this in the x direction, the problem is that v naught is a variable. I don't know what that is. So I can't do anything in the x direction because I've got two variables, and using the x direction alone, I'll only have one equation. If you want to use the kinematics equations, you're going to need 3 out of the 5 things to be givens. If you've got 3 out of the 5 things to be givens, you can get the other 2. looking at this, I've got displacement, I've got gravity, I've got time. Once I've broken it up into components, which is the first really big step for this one, if you see a diagonal velocity like this, oftentimes you can save yourself a lot of heartbreak by breaking it up into components using the x and y components with the initial velocity. Yeah. So, we can use these 3 out of 5 that we know to figure out what the other one is. Basically figuring out what Vy naught is. Once we know Vy naught, that gives us V naught as long as we have it set up like that. Once we know V naught, if we're looking at our x position, we can plug that in here. V naught will give us so that we only have our variable of delta x, and we can just find delta x. So looking at our y direction stuff first, we want an equation with displacement, acceleration, initial velocity, and time. Displacement, acceleration, initial velocity, and time. Plugging in our givens, and then solving. I'm actually going to leave some of these things as variables and other ones as givens. Great. Now I just need to solve for V naught, which actually isn't too bad. We add g over 2 times t squared to both sides. So delta y plus g over 2 times t squared equals V naught sine 30 times time. I don't know why I switched to theta. It's less writing, I guess. Divide each side by sine theta times t. Divide each side by sine theta times t. And we've got our initial velocity. So our initial velocity is equal to delta y plus g over 2t squared divided by sine theta times t, which is negative 15 times, plus 10 over 2 times 3 squared divided by sine of 30 times 3, which 5 times 9 is 45. 45 minus that is 30. 30 over 3 is 10. So 10 divided by sine 30, which I think is just going to be 20, but nice. So V naught for this one is 20 meters per second. Is that our answer? No, but it's getting there actually. It's honestly pretty close. What we can then do is come over to the x direction, because now we know V naught. So if we look at our x equation, it's that our distance is going to be equal to our velocity times time. Our velocity is V naught times the cosine of 30 times our time, which we know. Plugging in the rest of the numbers, because it's already solved for, we've got 20 times the cosine of 30 times 3. So 60 times the cosine of 30 is 52. And there's our answer. Whew. Much easier on that one when I don't accidentally make it so that it's algebra based on finding angles, which is going to almost always involve weird trig identities. So I don't know why I ever do it. I do know why I do it. It's just not a good idea. That's it. That's the video. I do want to go back through the process on this one real quick, though. So the big parts are you split up the x direction and the y direction. The kinematics equations work for the y direction. For the x direction, it's just velocity times time equals displacement in some variation. If you want to solve stuff on the y direction, you need to have three equations, three givens. If you want to solve stuff in the x direction, you're going to need two givens. If you want to relate them to each other, you need a point where you have like an angle and an initial and a velocity. That lets you reduce it from having Vx and Vy, which are two separate variables, to just having V naught if you break up V naught into components. So one of the first big steps, take V naught, break it up into the X and Y components, use those with your situations as either initial velocities or final velocities or something like that. Yeah. That's pretty much it. Hope you have a great day, and yeah. Bye, YouTube.